I'm Hannah Donner with the Collaborative on Health and the Environment. She enjoys bringing the latest environmental health science through our partnerships, calls, webinars, science serves, publications, and social media. I would like to welcome everyone to today's CHE-EDC Strategies Partnership webinar, which is titled Global Cancer Risk from Unregulated Polycyclic Aromatic Hydrocarbons. Our moderator is Sharyle Patton, Director of the Commonweal Biomonitoring Resource Center. We will leave time following the presentation and conversation with our moderator for a Q&A session. You may type in questions through the Q&A feature available on the menu bar at the top of your window at any point during the presentation. After the panel discussion and Q&A, our moderator will read out questions for our speaker to respond to. We will get to as many comments and questions as we can during the Q&A period. For those of you who have called in on the phone, we've posted slides to accompany today's webinar on our website. You can download these by going to healthandenvironment.org. Please scroll to the bottom of the page and select today's webinar. On our webinar page is a link to the slides. Everyone on the webinar right now is muted with the exception of our moderator and our speaker. This webinar is scheduled to last for 30 minutes and is being recorded for our call-in webinar archive. With that, I'll turn things over to you, Sharyle.
Thank you very much, Hannah, and I'm extremely pleased to present our next speaker to you all. This topic of PAHs, polycyclic aromatic hydrocarbons, has not been discussed sufficiently, I don't think, and we're all exposed to them. They are created when almost anything burns, and unless we understand exposures and the rate of cancer risk that might increase due to exposures, we're not doing a good job. So I'm going to introduce Dr. Selin to you. She's based at MIT. She's professor in Institute of Data, Systems, and Society and the Department of Earth, Atmospheric, and Planetary Sciences, and director of MIT's Technology and Policy Program. Her research involves modeling and analysis to inform sustainability, so decision-making, focusing on issues involving air pollution, climate change, and hazardous substances such as mercury. She received her PhD and MA in Earth and Planetary Sciences and BA in Environmental Science and Public Policy from Harvard University. Her work is focused on atmospheric chemistry, air pollution, as well as interactions between science and policy and international environmental regulations. She's received numerous awards, but I'm not going to read them all to you. We want to get right to her PowerPoint and her presentation, but I will say her most recent honor is she's a Hans Fischer Science Fellow at the Technical University of Munich Institute for Advanced Study. So Noelle, I'm going to turn this over to you. Thank you very much for joining us today. It's a really honor to introduce you.
Thanks for the invitation, and I'm really happy to be able to talk to all of you about our recent paper on global cancer risk from unregulated polycyclic aromatic hydrocarbons. This is work that was led by a former postdoc in my group at MIT, Jamie Kelly. He's now at University College London, and it was supported by the MIT Superfund Research Program. So this paper looks at PAHs, and PAHs are atmospheric pollutants that are produced basically when anything is burned, so burning of organic matter. And that can include things like wildfires, and it can include pollution sources such as traffic or other industrial sources. They're then emitted, and people are exposed when they inhale these PAHs. And this causes cancer. The inhalation leads to DNA damage, which subsequently leads to cancer. And so there are lung cancer risks globally that result from exposure to PAHs. And this exposure responds to both local sources and long-range sources. So both local and long-range transport of PAHs is cancer causing globally. And they're highly regulated pollutants, both on national and international scales. Showing one of the papers that has, previous papers that quantified global lung cancer risk from PAH exposure, that came out in 2014. But PAHs are a large class of substances. There are hundreds of them. And in regulating and assessing a large class of substances, it's typical to use an indicator substance or something that will tell you something about the class of substances, but be a little bit more tractable to measure or assess. And typically in the case of PAHs, the substance that's used is called benzoylpyrene. It's a 5-ring substance. And it's historically been often used as a proxy or marker for the entire mixture. This is the case for the World Health Organization. It's also the case for national regulations in the UK, the case for Canadian regulations, and also European Union regulations. And This is largely historical, but previous measurement studies have estimated that benzoate or BAP comprises about 40 to 80% of overall risk for PAHs. So the thought has been that even though this is just one of those many substances, it might be particularly important. The US EPA prioritizes 16 emitted PAHs, and these were decided on almost 50 years ago in the 1970s as a set of substances, and these are the ones I'm showing in this slide, that are of particular concern, of particular priority among the hundreds of substances. PAHs are also internationally regulated by the Convention on Long-Range Transboundary Air Pollution. That's what the UN Economic Commission for Europe. And they choose 4 of these substances to the right as indicators of emissions to monitor progress towards achieving reductions in PAH exposure as called for by the treaty. There are additional PAHs beyond the ones that are emitted, and there have been increasing attention in both environmental measurement and toxicology to PAHs beyond these 16 and beyond benzoate. And these include some of the higher molecular weight PAHs, but also PAHs that are produced in atmospheric reactions. So I'm showing here the flow chart that I showed you earlier, burning of organic matter that leads to emissions of these compounds. But what happens once they're in the atmosphere is they undergo atmospheric reactions. And one of those kinds of reactions is a nitration reaction. It adds a nitrate and forms nitro PAHs. And these products, these nitro PAHs, which are products of oxidation reactions that happen in the atmosphere, so we refer to them as oxidation products, they can actually be orders of magnitude more toxic than the PAHs that are emitted in the first place. And they in turn lead to DNA damage when they're inhaled and lung cancer risk. The question that we asked in our study is, what is the relative importance of all of these different PAHs to global cancer risk? And importantly, is benzoate pyrene a good proxy for that total risk on a global scale? And one of the reasons we were interested in this is that most global models of PAHs include very few species, and largely they just include benzoate pyrene. So one of the previous models that my group had put together, which was published almost 10 years ago, dealt with 3 PAHs, benzoate pyrene, and 2 others of different volatilities, phenanthrene and pyrene. But these other 2 papers looked at benzoate pyrene only and assessed the global lung cancer risk, and also examined some of the scientific uncertainties that affect relative lung cancer risk globally. So our question was, if you're just looking at one of these hundreds of substances and you're not looking at the oxidation products, does the story change? And is benzoate pyrene a good proxy or not? So in order to address this question, we constructed a global model to examine the relative impacts of different PAHs. And again, the previous global models had 1 to 3 PAHs, and we addressed 48 different species in our modeling. It's a global scale 3-dimensional atmospheric chemistry and transport model. The model we use is called GeosChem. It's widely used globally for a variety of different atmospheric pollutants, including toxic pollutants, ozone, particulate matter, mercury. We started with the 16 priority PAHs from the US EPA, because for those we had a global scale emissions inventory that was previously published from Shen et al. And what we did was we developed a chemical mechanism that we could apply for the nitro PAHs, so one nitration reaction, and a second generation of oxidation products, those with called dinitro PAHs, so 2 generations of those nitration reactions. And we developed that chemical mechanism and included it in our model. We evaluated our model against a global database of atmospheric measurements of as many species as we could find and did extensive uncertainty analysis. And then we went further to calculate what the expected cancer rates from these different PAHs were. And in order to do that, we had to use a different toxicity approach than had been previously used in some global model studies. Most previous global model studies used epidemiological estimates of cancer risk, and that's appropriate to the extent that benzoylpyrene is a proxy for that cancer risk, because it's based on some occupational studies that tied exposure to benzoylpyrene to cases of cancer. But in those studies, the people in these occupational conditions were actually exposed to a whole basket of different PAHs. And so with PAHs varying in their toxicity and their lung cancer risk, we wanted to figure out what the relative impacts of different PAHs are. So we used animal studies in which animals were exposed to PAHs individually. So we could then compare the relative impacts of those PAHs. So there's some technical differences in the total amount of cancer risk that we calculated. Again, we were primarily interested in the relative cancer risk here. And obviously, it's difficult to extrapolate from animal studies to human studies. But we designed this approach so we would avoid this double counting of cancer cases from multiple PAHs. If we added the epidemiological estimates to others, we would essentially be double counting. So I'm going to fast forward in this short talk to some of the key findings. And our key finding is that really benzoylpyrene is not a very good indicator compound to look at total risk from PAHs. And I'm showing two of our model results for the concentrations of these PAHs in the atmosphere, just as an illustration of the kinds of variability with in different geographical regions that these compounds have. On the left is benzoylpyrene, and this is usually used, again, as I said before, by regulatory authorities and also by scientists to represent the impacts of the entire mixture. And the background here is our modeled concentrations, and the little blue circles indicate the measurements that we have. And to the extent that they're the same color, then our model matches well with the measurements. And we do an extensive amount of quantitative testing of that also in the paper. But on the right, I'm showing fluoranthene, which is another emitted PAH, again, another one of those 16. And you can just see by eye that that both the levels of that PAH as well as the spatial distribution end up being quite different from that of benzoylpyrene. So again, those are going to be different in toxicity. So you have to apply the toxicity, but this gives us an indication that there might be some substantial variation here. And when we go through and we look at what people are exposed to among those 48 different PAHs, we can then calculate the fraction of global cancer risk that's contributed by benzoylpyrene versus the others. And that's what I'm showing here in the pie chart to the left. And we found that only 11% of global cancer risk was contributed by benzoylpyrene. And I'll remind you that the previous estimate that I talked about a few slides ago estimated from individual measurement studies in particular places that about 40 to 80% of the cancer risk was from benzoylpyrene. And this is really a function of fewer PAHs being measured in those particular studies, and also them not being representative of the global average. The other emitted PAHs, those are the other 15 of the 16 EPA priority PAHs, contributed 71% of the global cancer risk. And these oxidation products, these nitro PAHs, which are unregulated and largely unmonitored, there are very few measurements of these substances, contributed 17% of global cancer risk. That was a comparable number, potentially larger than benzoylpyrene, which is the one that's monitored, regulated, and used as an indicator. Benzoylpyrene has additional problems, though, and that is that we can point out differences in relative risk. So if you're just using benzoylpyrene as an indicator, we looked at two particular areas in our modeling. We looked at Hong Kong versus India. And if you look at relative risk and you're thinking about using benzoylpyrene as an indicator, it suggests a 3.5 times difference in risk between those two areas. But our method, because of the impact of the other 80+%, because of the impact of that other 80+%, suggests that there are 12-fold differences in risk. So using benzoyl as an indicator gives you basically the wrong answer in terms of the relative impacts of PAHs at different locations, because you're neglecting basically 90% of the problem, and that might vary differently than varying in benzoyl. So the second major contribution and finding of our study was that PAH degradation products do contribute substantially to this cancer risk. And I'm showing here on the left our concentrations of nitropyrene. Again, this is the oxidation product of pyrene. And again, the spatial distribution of these concentrations are very different from the parent compound benzoyl, and that's because they're produced in the atmosphere. So they might, for example, be more common a little bit downwind of sources because it takes some time to actually process in the atmosphere and produce these substances. And this is actually probably an underestimate. They're likely even more important than we calculate here. We don't account for other oxidation products of PAHs. We only look at the nitro products, not the oxy PAHs, the oxygenated PAHs, other kinds of oxidation products. And we also have a limited set of PAHs. We started with the 16, but there are other PAHs, other parent PAHs we could have looked at. And we had limited information on toxicity for those included. Again, we have 16 PAHs, 16 nitro PAHs, 16 dinitro PAHs. So of those 32 oxidation products, we only had information on toxicity for 12 out of them. So that finding of 17% is probably an underestimate of the total global burden of lung cancer that's caused by these substances. Again, the nitro PAHs are unregulated. And as you can see from the number of dots we have here in terms of looking at measurements that are available in order to constrain our estimates, they're largely unmonitored. There's only a few studies that look at their concentrations in the atmosphere, and they're not routinely monitored as part of atmospheric monitoring programs. So to sum up, we really are trying to think about the study in the bigger picture as trying to think about the best ways to reduce overall risk from PAHs. PAHs are a set of hundreds of different compounds, and regulatory and often scientific approaches have tried to reduce those and looked primarily at this one substance, benzoyl, for historical reasons. And what our study really showed is that it could quantify, our study can quantify the error in using this particular indicator substance as a proxy for the whole mixture. And it turns out it's not a particularly good proxy for actually figuring out what's going on in the environment and what's going on with global exposure to PAHs. So we have a number of suggestions based on this study, one of which is that increased scientific and regulatory attention, in particular to these degradation products, the nitro PAHs, as well as PAHs other than BAP, and also doing that at global scale, because there are a lot of heterogeneities and exposure across different regions to PAHs. We do definitely need more measurements to quantify this exposure. And we did, in this short talk, I'm not going to talk about some of the uncertainty analyses that we did. We found that a variety of different assumptions on how toxic and also the prevalence of these substances and some of the atmospheric processes really reinforced our conclusions that BAP isn't a particularly good proxy, but we would like to have a better and more quantitative constraints on what people are exposed to when and where. But one important aspect that sort of goes a little bit beyond what we were able to assess in our modeling approach so far is that we talked about the relative importance of benzoyl relative to other PAHs from location to location. But another way of thinking about it is to think about changes with time. So if you're only monitoring benzoyl and that's an imperfect and potentially very erroneous proxy for your overall risk, then changes in your benzoate-pyrene level, if your benzoate-pyrene level is going down, a regulatory authority might assume that, oh, this is good news. Total PAH-associated lung cancer risk is going down or up with changes in benzoate-pyrene. And our study suggests that's probably not the case, that monitoring changes in benzoate-pyrene, like relative importance of benzoate-pyrene, it won't be an effective indicator of overall change in risk. So you really need a more comprehensive approach. We're doing some follow-up work now to think about what this means for source reductions. Again, the overall goal is to reduce PAH-associated lung cancer, not just reduce BAP, which is 10% of the problem. So we're trying to figure out what this means for higher priority source reductions and what kinds of approaches can be taken to reduce that risk. And in general, we do need a better understanding of both exposure to mixtures and their impacts. We made a lot of assumptions about that these PAHs interact additively, and there's a lot of biological science that really needs to be done about how they interact in human bodies and lung cancer promotion. So with that, keep to my 20 minutes and wanted to make sure to leave time for questions. Again, thank you so much for your attention and interest in the study.
Thanks very much. That is just fascinating study that you're working on, and thanks for doing it. I'm going to just ask a few questions, and we'll see whether some questions will come now from our participants. And participants, please go ahead and put your questions in the Q&A section at the bottom right-hand side of your screen, and we will get to them as we can. But I wanted to just ask you one question, which is these PAHs, how far can they migrate from their sources? And how long do they last? I know they break down in the atmosphere once they're there. They're part of smoke. But if as an ingredient in smoke, how long do they stay in that smoke plume? And I know there's a lot of variability in that, but can you kind of give me a ballpark figure of the maximum distance they might travel compared to minimum?
So we do find that PAHs, despite their relatively short atmospheric lifetime, can travel quite long distances. So some of our earlier work looked at long-range transport of benzoate-pyrene and the other two PAHs to the Arctic environment. So they can travel long distances. Obviously, the highest concentrations are going to be near the sources. But they're a global problem, and their inclusion on the Convention on Long-Range Transboundary Air Pollution really underlines the fact that they can cross borders and can pose risks far from the site of their emission.
Okay, and you mentioned that you're just beginning research on this, but could you just talk a little bit about what the high priority sources are?
So again, thinking of what I meant by saying that is, there are different kinds of approaches that you could use to understand what's causing emissions. So, for example, different sources could include sort of industrial sources from vehicles, sources from wildfire or other burning, or biomass burning in general. And in terms of regulation, you would want to address the sources in particular regions that are most impactful. You would want to go after the sources that are causing the most toxicity first, and try to have the most bang for the buck in terms of the kinds of source reduction measures you put in. So the question is, if you're ranking those sources based on BAP versus ranking them based on the entire suite of PAHs to which people are exposed to from them, it might actually change which sources you might go after first. And that's really an open question that we're addressing in future work.
We look forward to further information about that. One question from BJ Cummings, I'm going to just read it to you. Cleanup levels at hazardous waste sites around the country are being changed to reflect the recent IRIS reassessment of BAP and 6 associated CPAHs, which concluded that they are 7 times less toxic than previously thought. Can you address what this new study indicates about the confidence we should have in that IRS determination?
Yeah, so this study doesn't directly look at the expected toxicity of individual PAHs. And again, we'll look into those updated values. What we did do is look at the relative importance of the 16 PAHs relative to their degradation products. And so there are all sorts of uncertainties about the toxicity and how many cases of cancer you might expect. But what we're saying here is that given that this is a priority pollutant, how good is one indicator relative to another. And also the sort of under-assessed nitro degradation products. Where are they in the atmosphere, and how much are they contributing? So again, if you're changing the relative importance of those different PAHs, we can take that into account, but it still pretty much says that benzoapyrene is not a big contributor overall compared to some of the others. Again, because you would move up and down according to those estimates.
Okay, thanks for that answer. Very good. From Tim Rogers, how do the 16 US EPA priority PAHs perform as a proxy for overall risk? Is there a minimum number of real or hypothetical compounds explored in chemical space, e.g. KOA-KAW or something that would perform well? Does that?
So yeah, we weren't actually able to look at the 16 priority PAHs relative to other emitted PAHs, primarily because we don't have emissions inventories for those other PAHs. So what we do is, we did find that about 80% of our risk was from the parent compounds and 20% were from the degradation products. So it does suggest that even for those 16, that the degradation products are important. For overall risk, I think there are some studies in particular places that give a sense that there are other non-16 PAHs that are vitally important. And that really, I think, underscores our analysis that you really want to go after the whole mixture, including the degradation products, and that maybe using the subset isn't necessarily an ideal approach.
Thanks for that answer. Would you suggest that biomonitoring programs should start testing for the breakdown products?
So certainly in atmospheric measurements, yes. I wouldn't necessarily, the biomonitoring programs, I'm not sure what you would monitor in that's kind of beyond my area of expertise in terms of what you would monitor to assess exposure in biological samples.
Mm-hmm.
But certainly looking in the atmosphere, I definitely think that more studies should address the nitro PAHs and other degradation compounds. We could very much use more measurements as we showed here. These were the ones that we could find that we could use in terms of our constraints on our model for nitropyrene, for example.
Okay, I think that's really interesting information to have. Okay, we're just about 2 minutes away from the end of this presentation. Let me just check once more about the questions. And our questionnaires are saying thanks very much for your responses.
Yeah, I didn't actually answer the second part of Tim's question of the hypothetical compounds exploring a chemical space. That's a really interesting point. And we did some work in our earlier study looking at differences in volatility and their implications for transport. But that's a great idea, and we'll definitely look into that more.
Well, great. Perhaps as you look more, we can have you back in terms of what your findings are as you move forward in all of this. Here's from Kimberly Terrell. Can you tell us anything about the relative odor thresholds of the 16 PAHs, especially benzopyrene? Are residents likely to experience noxious odors from levels of PAHs that might be of health concern? So how does the common citizen recognize that their exposure?
Yeah, I don't think we're talking about levels that you would be able to perceive sort of in odor. I think if that were the case, that would be really bad. We're talking about background levels that people are exposed to in the ambient environment. So the kinds of levels that we are able to assess here are the kinds of levels that you would breathe just going outside on a normal day in the air pollution environment that you're in, which may have associated higher levels of air pollution depending on where you live. But this wouldn't necessarily be perceptible as PAHs. You might see more particles in the atmosphere. You might see a sort of generally less air quality day, but PAHs wouldn't be sensible other than by measurement techniques.
Okay. Thanks very much for this excellent presentation. And we look forward to hearing more from you. It's great to see you again, Noelle. So thank you very much for joining us today. It's been my real honor to have you on. I'm very excited about this webinar, as you well know.
I'm going for the invitation.
You're welcome. I'm going to turn the mic over to Hannah, who's going to do the closure for everyone.
Great.
Thanks again.
Thank you so much, Sharyle, and thank you, Noelle, for your presentation, for the great work you're doing. So today, this is our end of our webinar. We're approaching the end. Video recording will be available on CHE's website soon. And tomorrow you'll receive an email containing a link to the video. Our next CHE Alaska webinar will take place on Thursday and is titled Addressing Root Causes and Preventing Breast Cancer, a new toolkit in breast cancer action with a precautionary prevention-oriented approach. Details are posted on our website at healthandenvironment.org. If you are new to CHE and would like to stay updated about upcoming events or more, please sign up to receive our newsletter by selecting the Join Us tab at the top of any page on our website at healthandenvironment.org. Additionally, if you appreciate the CHE Partnership webinars bringing the latest environmental health research for free, we encourage you to support CHE's ongoing work by making a tax-deductible donation via our secure website. Again, our website is healthandenvironment.org. With that, I'd like to thank our speaker, Dr. Selin, Noelle, for taking time today to present, and to you, Sharyle, for your excellent moderation. Thank you so much for joining us. We're wishing everyone much health and wellness. Stay well and take care. Have a great day.